然后看的名字，你说你在有地听而已。是啊，不是啊，那个听是5月6号。就是分享，要3个人啊，抽中的，我个人投标准，这样。5月6号的，5月6号的，我不知道。我给你看这个，这个就是当初讲到第4页的10页。你是说你们那个分销？你们讲另外一个，谁？
上课前来不及写加分题，好，没关系，我们就直接开始上课。So we start the lecture for today. I hope. Let me check if the live stream is working. Yeah, it's working. So it should be okay. Then I start. Okay. We stopped at the electric motor last time, but since it's already 1 week ago, so I think let's just play the essential part of this movie one more time, and let's just remind ourselves how the electric motor work before we start with the analysis. So I skipped the part with the construction, but the point is just like there is a magnet, and you can imagine now the magnet is creating a magnetic field going this way. Most of the part of the magnetic field goes this way, and it can rotate, it can go this way like this, and you can try to imagine the magnetic field in your head. And here is the coil. You can wrap it up by yourself. And here is a connection between the thin wire and the thick wire, and because it's directly attached to the battery, so there is current running through the coil, and the circuit looks this way. So it's the construction is like this. And if you set it up this way, and we can see that now the coil then it starts to rotate. And this is the simplest electric motor. And the electric motor is basically everywhere in modern world. There is electric motor in cars, in motorcycles, in train, and basically everything that moves and everything that is like a car, like a vehicle. Then every kind of traffic tools, and all of them are sort of driven by electric motor. And this is, of course, there are some other technologies, for example, to make the magnetic field stronger, to make the rotation regular. There are many different kind of requirements, but the basic concept is just like this. So we can see how it works. So let's just play the last part. But this time, when you're looking at the motion, just pay attention to the direction of the magnetic field and the direction of the rotation and the direction of the current. The current, the rotation, and the magnetic field. Yeah, 3 components. Please take a look at them. And you can do it at home by yourself. It is a very lovely and very interesting experiment. I will show you some other electric motors like this, a spinning heart. We will look at it later. And I strongly encourage you to do it, and then maybe in the coming Mother's Day, and you can give it to your mom. I'm sure she's going to be very happy. And yeah. 等一下，我们今天先看最基本型的，就是你的线圈是水平的架着，然后水平旋转，因为这个架构下面它的力学比较好分析。然后今天上课的最后，我会给大家看一个是你的 motor 是直立起来的那种，然后像那种你就可以做很多可爱的小花样，比方说你可以把你的线圈折成爱心的形状啊，然后妈妈节你可以送给妈妈，你就插上去那爱心的形状，妈妈一定很高兴。有做的话可以带来给我看，可以加分。好，所以这是好，我们刚刚就看了，我们现在我进入状况了。好，你们要进入状况。So now here's the analysis of the forces on the coil. So let's take a look at the forces created by the current and the magnetic field. So now the configuration is a little bit changed. So if you look at this, you can see that in this picture, the magnetic field is going this way, from the bottom to the top. But when we are doing the analysis here, now the magnetic field is going from the N pole to the S pole. So the direction is changing, like it's like this. Now the direction is like this. The configuration is different from the one in the video, but just change your view a little bit, and I'm sure you can catch up. So now this is the direction of our magnetic field, the vector B. And this is our coil. So this is like a loop, and the current is running this way. So now the running of the current is clockwise, right? Yeah, the current is clockwise. And let's focus on the wire here, this one. So let's take a look at this one first. So we can apply the Lorentz Force Law. So the direction of the force is I cross B. So if I put my 4 fingers, if I use the right hand rule, I put the 4 fingers along the direction of the current, the red arrow. Then I rotate my hand and let my 4 fingers point to the direction of the magnetic field, the blue one. I rotate my hand from the red one to the blue one. Then the direction of my thumb is the green one for the vector force. So you can operate it. You can operate the action by yourself. Then for this piece of current, the force on that current is pointing upwards. So this is on one side of the coil. And now you have to keep your attention and keep your track of derivation. So let's change our attention, switch our attention on the other side of the coil, this one, the wire which is closer to the N pole. And now if you use your right hand rule again, so if I used from the red one to the black, from the red one to the blue one, oh, this way. And now my thumb is pointing downwards. So now we do 2 complicated actions. And if you jump out of the picture a little bit. And if you look at the direction of the two green arrows, you can see that on one side it's pulling the coil upwards, on the other side it's pulling the coil downwards. So the push and pull of the two forces is turning the coil around. So this is how the electric motor works. This is the reason why when you put a coil inside a homogeneous magnetic field, and then the coil starts to spin, and you can use the right-hand rule to check the direction of the spin. And for the current on this side, this is a little bit hard to describe, so I use my mouse to point it. If you look at the current, the current here is parallel to the magnetic field, though the directions are opposite. But in this kind of situation, this kind of current doesn't create any force. The magnetic field here doesn't push this kind of, it doesn't have the action on it because of the Lorentz Force Law. So here it doesn't experience any forces, and for the current here and here it doesn't experience any forces too. And here is a little bit of connection and junction, so it just experiences the same force like the two green arrows. So this is why the coil rotates, and this is the basic concept of every kind of electric motor. So this is how the physics works, and here's the detailed, and now then we have to do some derivations based on the symbols. So here is just to remind you, this is how the magnetic field look like in your configuration. So the blue one, and then this is just a field of magnetic field, and it's penetrating through the coil. And here, this is the direction of the current, and this is the forces. And we are going to define one more thing. So here, pay attention to the length of the coil, this one. So this is the coil, this is the wire which really experiences the forces, and pay attention to the length. And here is the other one with the same length. So this is the geometrical factor of your electric motor. And now here are the complicated things, so be careful. So here, the forces which pulls or push your coil, and it's spinning with respect to an axis， 就是你的旋转，大家可以想一下，我们上学期在讲 rotation， 在讲旋转运动的时候，每一个旋转我们都要先找到它的轴，对吧？ So if you remember, every time when you start an analysis with a rotating systems, the first step, look for the position of your rotational axis. So in this system, the rotation axis is this one. I'm pointing it with my mouse so you can follow it. This is the center of all of the rotations. And here's the length of the current, which changes the force. You can see the length, the magnetic field strength, and the current. So it changes the strength of the force. And this is the arm of your rotation, this one, from here to here. And because the width of your coil is W, so the arm is W over 2. 好，这边有一个比较难看见，但是你马上经过提醒，你马上就看得见的事情，就是你的线圈旋转的轴有没有？然后呢，如果说你的线圈是对称，是正方形的，然后呢，它的长度这边是 W 的话，这个旋转的旋臂啊，手背，我突然之间忘记那个中文要怎么讲，但是你的旋转的手臂就是从旋转的轴到这个被拉的电线，这条长度，这是 W 除以2。And then let's calculate the torque. Now we are analyzing the rotating system, so now we have to analyze the torque. The torque is equal to the force, outer product, and the arm. So this is where we start with. And the force is ILB. So this is because we apply the Lorentz Force Law. And arm is W/2. And just as I explained before. And outer product gives you a angle, sine a certain angle. And let's take a look at the angle later. And okay, but be careful. We have one side of forces and the other side have exactly the same force. If your coil is symmetric. 如果你的线圈是对称的哦，如果是对称的话可以这样子啊，如果不是对称的你就要用积分。We have two sides, so we have to multiply it by 2. So this is the total torque applied on your spinning coil. 所以你现在这样子推导出来哦，这一连串的这一串这些数字，这个，然后这个 A 是 area. The A is area because the length and then the width, and it gives you the area. Okay, so this is the symbolic representation of the total torque, which drives your coil spinning. And now we have to change our perspective from here to here. 所以，然后你现在要稍微改变一下你的观点。我们现在都是用俯视的观点在看你的线圈有没有？你现在走过来，走到转的轴心的这边，然后呢，用这样子的方向看进去，就是你的眼光往这里这样看进去，然后意思就是你看的就是你的线圈的屁股。And here is a projection or diagram which helps you to look at all the angles. 你可以看这边哦，就是这样看你绝对是看不出来的啦，头很昏。但是如果说你画一个投射平面图的话，那你就可以看到呢。So this is the coil. From here to here is from here to here. And here's an angle alpha. So if you look at if you start all the derivations from the horizontal axis, and when you fix yourself in a certain time, and here, this is the tilted angle of your coil. This is alpha, and in three-dimensional plot, alpha is here. 就是在三维空间里面的 alpha 是这个角度。那如果说你看的是二维投射平面图的话，你就会看到 alpha 是这个角度。And then here let's take a normal vector. The normal vector is normal to the area of your coil. So the normal vector gives the angle 90 degrees, and this angle, this angle is theta. 好，我们现在要重新稍微定义一下你的坐标系统。Okay. And if you get into the situation, and let's look at the plot this way and let's take a deeper look at it. So here is this one. The force is applying on your coil this way. It's pulling upwards. But the rotation is going, the forces of your rotation, which drives your rotation, is going this way. So the force for the torque should always be perpendicular to your arm, this one. So when you are really doing the outer product for your torque, you are actually taking this force and the outer product of your arm, but the angle for your outer product should be this one. This angle is the theta in our derivation before. Yeah. You have to, usually I think about it this way, because if I follow the mathematical equations, I always confuse myself. But every time when I'm looking at this kind of schematic diagrams, I always think that, okay, now the rotation and the force should be going this way and to make the motion circular. So I just simply take a projection of the force on this direction. So what is this theta? What is this angle? And this angle is just simply equal to the theta here. Because if you look at the geometry, then you should get the answer. You can see that this is alpha plus theta is 90 degrees, and this is 90 degrees, and this is 180. So this should be equal to theta. 我通常在看外积的时候，然后我都会觉得很混乱，因为一下 sin 一下 cos， 然后就会觉得很痛苦。但是我通常在看这种事情的时候，我的想法就会是，我的转轴在这边，然后这个是我转的手背的长度。那么我如果是一个，你看这边它是一个圆周运动嘛，那如果是圆周运动的话呢，那我拉扯线圈的力就必须要是垂直于我的旋转轴的方向，就它必须要是垂直的。那我现在这个力呢，如果我把它做一个向量分解，就是呢有一部分的力是在垂直于转臂的方向，然后呢以这个状况有一部分的力是会这样往外拉扯啦。但是呢我需要知道的就是我把我的力投影到垂直于转臂的方向，这个就是实际上在拉扯我的旋臂在做圆周运动的力。有一点点复杂，大家回去可以静下心来思考一下，你就会知道了。好，这也是为什么电动马达的分析常常都会有一点痛苦，因为你要把你的转轴跟转的方向，然后你要先搞清楚。Okay, so now then I can get the torque. The torque is then W over 2 cosine alpha. So this is the projection of my force onto this direction. And cosine alpha is actually equal to sine theta, if you apply the trigonometric rules. Cosine alpha wait a second. This is theta. Theta. 等一下哦，讲讲我自己有一点混乱。等一下。W 除以2的 cosine alpha 其实是这条长度，然后呢，它力就这样拉上去，没有错。然后呢，如果说 cosine alpha 是这里，然后好，不好意思，我再加一个注解。我自己有一点点乱掉，但是我决定要加一个注解。cosine alpha cosine alpha 是这个角度。Cosine the alpha is this angle. How? Alpha is this angle. And sorry that the plot looks very busy. And cosine alpha is this one. OK, cosine alpha 就是这段长度。So this is the length of cosine alpha. And here's the force created by the magnetic field. Okay, this is the way that the author of the plot is thinking. So this is the force. Okay, so this is how his torque works. So we have ILB and W over 2 cosine alpha. So this is how its torque working. But this length is exactly the but if you look at this angle, this one, yeah, this one. The angle theta here, if you take a sine theta, is giving you exactly the same length. So I hope this is clear enough. Like this. Yeah. So that's the reason why you can do a transformation like this. You can do a transform like this. You are transforming the angles. We are doing a complicated transformation like this because people like to use a magnet, a magnitude which is called a magnetic dipole, to do the analysis. So they like to change the focus of the angles. 我们现在要做这么复杂，然后看起来毫无意义的动作，是因为在更复杂的分析里面，大家喜欢用一个叫那个磁矩 magnetic dipole 的量，然后那个磁矩它看的是这个 normal vector， 然后跟水平跟磁场之间的夹角，然后这个磁矩 normal vector 的夹角跟磁场的夹角是 theta， 就是这个角度。所以我们要做，大家喜欢做这么复杂的事情。It's because when we are analyzing complex systems, we like to use the magnitude, the magnetic dipole, and the vector of the magnetic dipole is this one, which is perpendicular to the area. And usually we directly take the torque by the outer product between your magnetic dipole and the magnetic field. Yeah, and this is the angle theta, and the angle theta is this one. So that's the reason why we do a complicated transformation like this. Yeah, I tried my best. I hope you can follow. Then the next step. Yeah, so this is a torque that we just derived. The L and W gives you the area, and the theta is the angle between the normal vector and the magnetic field. Okay, clear? And here is this is what I just said. This is the area and gives you the A, and the current I and A is defined as magnetic moment. 所以这边我们做一个新的定义，我们把线圈的面积，然后还有乘上电流这个奇怪的单位，我们把它定义为磁矩。这个就是假设说你现在你要处理的是一群电动马达的问题的时候，这个就很好用。然后我们再讲那个什么磁性系统，然后 spin 啊，因为我们处理都是一群电动马达，这样比较好处理。不然的话，每一个线圈你都要拿来分析的话，它受不了。Okay, and if you look at the equations here, and actually we can change the torque into the outer product between a magnetic moment and the magnetic field. Yeah, this is the magnetic field, and I and area and the normal vector is giving you the magnetic dipole, which is vector mu. And outer product of vector mu and b gives you the sine theta. So this is how we do the arrangement. Okay. And if you are in the occasion, sorry?
How come tau isn't a vector?
Sorry?
How come tau isn't a vector?
Tau is a vector. Tau is always a vector. The torque. The torque is the arm, the force, and the arm and force. If I rotate my hand this way, then the tau is a vector normal to the arm and the force.
How come it doesn't have arrows?
Because I omitted it. Sorry, because I was lazy. I didn't write the vector form of the tau here. It should be a vector. Yeah, you're right. 刚刚同学问的是说，为什么那个tau不是向量？因为我很懒，因为我没有把向量的方向写上去。我这边写的直接是那个tau的强度，这里是tau的强度。然后 mu cross b，mu cross b，mu cross b， 那现在的tau是往直面指进去。What that mean? Okay, it should be a vector. Yeah, it's easy to change it, so I do it right away. And now the direction of the tau is this way. It's pointing into. But I don't know where to put it, sorry. I don't know where to put it on the plot, so I just put it here as a reminder. Okay. U and B. Yeah. I think I'm right. Okay. And if in some situation like you need to calculate how much energy should you put into the electric motor to drive it working, then you have to calculate the mechanical work. This is the definition of the mechanical work for rotations. So we have the torque. This is how much angle you just been rotated. Yeah. And from 0 to pi, so this is from here to here, a half round of the rotations. Then you just put in the tau is equal to this one, so we can just put in right here. So this is the mu and b and sine theta. And this is from the outer product and d theta. And the integration of this one is giving you cosine theta. Yeah, and cosine pi minus cosine 0 gives you 2. Yeah, and just mind the positives and negative signs here. And if you do the derivation by yourself, and then you can just figure it out. Okay. So to be very honest, every time when I'm handling the rotational problems, like the energy taken by a magnetic moment, I'm not able to derive it like this by myself. I need to have a slide like this by my side, and I have to follow it step by step. Yeah, I have to really say the truth, because the directions of the vectors are too complicated to remember, really. So if you cannot really remember, you don't really need to worry. You just need to remember, there is something called magnetic moment, and there is a way that we can handle a lot of things at the same time. If you need it, and then you just take it and then just follow the right procedure. 然后，如果你现在发现说你已经跟不上了，请不要慌张，因为我自己这个上课的人，我自己也是跟不上的。对，我是因为我在做课堂的，像你刚刚也看到，我就乱掉。我每次看这个时候，我没有记得过，从这边到这边到这边到这边，然后这个结构分析到这边，我相信应该没有人记得啦，除非那个老师是他讲这个讲了100遍，他已经背起来了。正常人，如果你同时在处理很多事情，你是不可能记得的。那所以你不要慌张，我不记得的事情，我就不会考大家。对，那我觉得这件事情的重点就是说，你要知道我们在分析一个有旋转的东西的时候呢，我们就会跟随这样子的思考模式去做一些推导。你只要知道说，我们有一个东西叫 magnetic moment， 然后呢，它的经过一串推导之后，它可以简化成你只要关注电流跟线圈的面积就好了。好，你只要记得有这件事情，那只要你以后有遇到需要分析电动马达的状况，你就把这一套思考的流程，你就把它从你的笔记本里面翻出来，你就对照着，然后慢慢完成你的推导就好了。请不要对于这件事情过度的焦虑。So in situations like this, what you need to do is you have to really be concentrated to make a procedure of thinking by yourself, and you can keep it somewhere in your notebook or keep it in your computer. And later on, when you need to model something like this, or when you need to solve a problem like this, you can just take your notes and you just follow the procedure and finish it with full concentration, and that's it. So you don't need to be too anxious about I can't remember the procedure, I don't remember all the hacks and all the techniques. No, you don't need to be that nervous about little things. Okay. And here is another video, and this is a bonus for you. Yeah. So we just learned how the forces are applied on the coil, and here I'm showing you some coils with other structures. And please analyze it, and please explain why it's
Good
spinning
grammar and spelling.
And you can leave your thoughts and leave your comments or leave your schematic diagrams, anything on our new E3. And if you do it in a good way, then you can get bonus from 1 credit to 5 credit.
Are important, but if you want to write essays that inspire, messages.
Is this one. So you can see that in our derivations, we were handling current flowing like this, and the magnetic field is going this way in our examples, in our derivations, right? But now we are changing the geometry to another one. So you can see that now the current is still running this way. Yeah, it's connected, it's running this way. But now the magnetic field is going this way, like this. I suppose the magnetic field is going this way. And how come the heart should be spinning like this. And here's another example. So this is a question for the bonus. So please analyze the forces applied on the heart-shaped coil like this in this kind of magnetic field. Please analyze the direction of the current, the direction of the magnetic field, and the direction of the force, and explain how the heart is spinning. Or if you want to do it in an easier way, then you can analyze this one. They are mathematically the same, though the geometry is different, but the mathematics is just exactly the same. Yeah, so you can just analyze it and then you can leave your comments on our website, but I will ask the TA to give you credits. And if you want to do an experiment by yourself, and you're very, very encouraged, and if you do it, then you can bring it here and show it to me, and we can play it together, and you can get extra bonus. 所以这边是我们的加分题咯，请大家分析这种直立式的 monopolar， 就是单极 monopolar motor， 就是请大家分析，在比方说这个爱心的，请大家分析在这里你的磁场的方向是怎么指的。我希望你可以把整个磁场都画出来，不是只有画导线上面的磁场而已哦，因为你只画导线上面的磁场的话，这题是解不出来的。请你分析磁场它的整体的结构，然后请你分析电流的流向，然后请你分析 I、L、BL 是长度嘛？好，然后呢，磁场的方向、电流的方向，还有力的方向，就从磁场跟电流的方向，你一定可以推论出力是怎么是加于这个爱心上面的，然后为什么爱心会这样旋转？那如果爱心对你来讲，你觉得太复杂了。想不出来，你可以从圆圈方框框开始。So you can start with this one. It's also it's 你可以用这个去想，也可以。爱心跟圈圈在数学上来讲应该是一样的。好，那如果你自己想要做实验的话，那我也非常鼓励你自己做实验，它还蛮简单的。你有做成功的话，你可以带来跟我们分享，好，跟你玩一下，然后我们可以再多做加分。好，那规则也是跟以前一样，就是你把你的想法、你的推论，你把它整理好，然后把它上传到那个在我们 UE3 的讨论区里面，然后我会去请助教给你们分数。那如果你有做实验的话，就会再有额外的加分。好，但是我题目还没出好，等我一下，我回去我再把题目写下来。好。Then we come to the theory. Here's the Gauss law for magnetic field. So let's just review the sources and the magnetic field. So we started a current on the wire, and we can see the magnetic field is spinning in a circular way. And if we have a loop of wire, then the magnetic field is going on a bipolar way, which looks like a butterfly. So if we have the solenoid, then it's also a butterfly shape. The bar magnet is the same, and the earth is a butterfly shape. So here, let's just look at the flux of the magnetic field through a closed surface. Just in your head, you try to imagine you have a big balloon and you wrap your magnet up. You wrap it up and then you try to look at you just look at the magnetic field just like flows of fluid, flows of water. And let's calculate the flow of the fluid flowing in or flowing out of the closed balloon. So if we wrap a bar magnet up, if you calculate the magnetic flux, we are not calculating it right now because we haven't learned the mathematical technique to solve your magnetic field, but I'm sure you're going to do the calculations on in electromagnetism in the second year of your university. But you will finally prove mathematically that here, this is the magnetic field going out of your closed balloon, but it always turns around and come back at the back of your magnet. And if you follow the amount of fluxes flowing out and the number of fluxes flowing in, you will find that the flux out is always equal to flux in. OK， 好，你现在可以想象一下，我们用一个封闭的球面把你的磁铁包起来，然后呢，就像我们计算电场的通量一样，我们也来计算磁场的通量。但是我现在没有办法用数学的方式证明给你，因为我们现在拥有的数学工具没有办法用公式把这种双极式的场把它表现出来，我们现在没有办法用数学证明。但是呢，你到最后你就会发现一件事情，电磁学一定要证明这件事啦，会很痛苦，先跟你预告。然后呢，你就会最后就会证明说，你的磁通量呢流出去的量，你会发现其实我们的磁场其实是一个它磁场是一种很封闭的东西。你的向量从封闭曲面流出去之后，虽然你这里看不到，但是它一定是跑到一个很远的地方，转一圈，然后从磁铁的屁股灌回来，然后你所有的磁场线都是这样出去，然后这样回来。那你如果说去计算它的磁通量的话，就会发现你流出去的磁通量跟流进来的磁通量永远都是一样多的。好，然后我在这里特别跟大家讲一件事情，我刚刚很小心在使用我的用词，我没有说磁力线一定是一条线，然后一定是连续，然后一定就是比方说这里是4根出去，一定是4根回来，我不敢讲这样子的事情，因为那个在数学上面其实那样子的观念很狭隘，这样不太对。好，就是因为那个观念太直观了，所以有很多时候，好像从国中啊、高中都会教大家一个概念，就是什么磁力线，然后或者是电力线，一定是有头有尾，然后不会断掉，等等等等这样子的想法。可是其实那样子的想法是法拉第的想法哦。但是大家要想，法拉第是一个没有受过教育的人，他没有学过数学，他会那样子想，是因为他观察，还有他用一个图像式的方法去解释，所以他讲出了那样子的想法。可是等到我们进入马克思韦的时代，进入向量分析数学的时代之后，所有的磁场跟电场，它只是一个方向跟一个强度。就没有所谓的什么电力线或磁力线这种东西了，就是你就是一个方向一个强度，那你会算它的通量，可是算通量并不是算你的电力线或磁力线有几根，不是哦，所以请大家不要被那个观念局限或是困惑到。然后跟大家讲一个算是我的小秘密，我高3我是没有念的。就我的高3我是直接就是跳级，然后就去考大学，所以我的高中的自然科是我自己念的。然后上了大学之后也跟大家讲过，那时候我的电磁学老师就是念讲义嘛，然后那时候我跟不上啦，就是我跟不上他的讲法，所以后来电磁学等于是我进研究所后自己念的。所以我的电磁学我一跳进去，我就是从向量分析去学这些概念。 结果等到我回来，我变成我要教别人电磁学的时候，我的学生会跟我说，电力线一定是有头有尾，不会断掉。我就哈，因为我没有学过这件事情，对，所以后来我的学生来跟我讲这件事情，我都觉得非常的惊讶，就是是真的吗？我还真的回去查了一下，说这个概念到底是哪里来的。对，那其实那个是法拉第的想法，就是那是法拉第他在画图的时候，他心里觉得事情应该是这样。对，但是其实我们现在离法拉第的时代已经很久了。对，所以我们现在在分析电场跟磁场的时候，我们看的只是一个方向，然后我们看的是在那个方向上面我的力有多强。对，所以请不要觉得说，电力线是有头有尾，然后我要算几根，然后很多根就表示很强，很少根就表示很弱，那个观念不太对哦，不太对。然后你的电力线看起来很密，你去量就会很强，那只是一个巧合而已，那是巧合，所以请大家不要被古老的观念捆绑住。好，so I just said that in the educations, and sometimes people will say that electric field lines or magnetic field lines should be a line, it is continuous, and if it comes out, and then it should be always linked like this, and then coming back. And if we have a lot of lines in a small area, that means the field is stronger, and that is just a coincidence. But actually, when we are really working on the distribution of forces, and that is not that way. So when we are looking at the electric field or the magnetic field, which is the distribution of directions and strength, we are just looking at the direction and the strength. And actually, all of these lines, and they should be broken into little arrows, and each arrow is pointing to a direction, and then you should give it a color code to tell everyone the strength of the force. And you shouldn't link them together and give it a mysterious property like it should be linked together. It has a head and it has an end, and they shouldn't be broken like this. No, that is not the property of field. Yeah. When you're analyzing the field, it's just the direction and it's a strength. You have to look at the direction and the strength by the actual number, but not the density of the lines. Okay. And we just analyzed the whole magnet, and then we just take a look at a part of the magnetic field. So if you just draw a closed boundary and you analyze the flux of the magnetic field flowing in and flowing out, definitely you'll find that the flux going in is equal to the flux going out. And if you analyze it here, you should give you're getting the same conclusion. Okay. And if you look at it like this, and then you get the same conclusion. So then we can compare the electric field and the magnetic field. So for the electric field, you can see that the electric field are going in a way like radiative, like this, isn't it? We have a source at the center, and the force is going out in a straight line, and it's going like a star, radiative star. And if we take a closed surface, we wrap the charges inside, and then if you calculate the flux, the electric field flux, and you just integrate it all over the closed surface, you can find a relation with the source. And if we do exactly the same thing to the magnetic field, you'll find that the number is always 0. The total magnetic flux flowing in and out of the closed surface, if you sum them up, it should always be 0. 所以这边是一个电场跟磁场的比较。对电场而言的话，如果你把你的电场源，就电荷啦，如果你把它用一个封闭曲线、封闭球面，你把它包起来，然后呢，你就会发现呢，你的电场通量一定是正比于你的电荷，就是高斯定律给电场的高斯定律。但是你如果对磁场做同样一件事情，你到最后就会发现，你的磁通量永远都是零。这是一个很奇怪的物理现象，到现在还是有很多人想要打破这个定律。For the moment, there are many physicists who want to break this rule. They want to break this rule, this one. Yeah, because for physicists, it's so strange. Physics doesn't like a symmetry. So they try to develop every kind of theory to explain why we don't have a magnetic source like a point, and they would like to explain maybe in some special conditions then we will have a monopole of magnetic, but because of blah 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 blah, and we don't see it in everyday life. Yeah. And the famous physicist Dirac, he looked at it in a very, very cute way. He said that if I'm flying here and look at my magnet this way, and this one's the head of a magnet, and you see all the lines going out like a flower, isn't it? And it just exactly looks like a monopole. So he just looked at it by the geometrical problems. 就是有一个物理学家叫狄拉克，狄拉克在近代物理学里面是一个很重要的鬼才。然后呢，他面对这个问题的方法，就是他想象它是一只小虫子，它是一只小小的蚊子好了。那只小小的蚊子它在这里滋滋滋在这里飞来飞去，然后那个蚊子往这里看的时候。然后呢，他想象说，我的磁铁是一个细细长长的螺线管，然后那个螺线管很细很细很细，所以他看不见。然后从螺线管炸出来的磁场看起来就会像一个磁弹机一样。然后瞬间就有人问他，所以你的意思是说螺线管嘛？那就是你在这端一定会有一个这样炸出来的磁单极，那另外一端宇宙的另外一端一定会有另外一个磁单极，然后方向跟你现在看到是不是相反？然后他们就是在宇宙学上面，他们就在推论说，或者是在量子力学的理论上面，他们就在辩论说这件事有没有可能发生。好，就是关于磁单极的理论。我是觉得狄拉克的观点很可爱啦，他就说，我如果就是我把我的螺线管这样，我就这样看着它，这看起来就像一个单极一样啊。然后他的问题就是，所以磁单极一定要成对出现哦，一定要一正一负，对吗？然后狄拉克就说对，然后那你可以看到我们在电荷的时候啊，电荷它是有时候会是正电荷单独一个出现，负电荷它会单独存在。大部分啊，你如果是人工的去刺激它，然后它一定是以正负出现。对，但是我们在很自然的状况，你没有去刺激它，我们还是会看到电荷就是正的自己一个人跑来跑去嘛，或是负的自己一个人跑来跑去。这个对于物理学家也是一个谜题哦。你会发现物理学家的谜题都看起来都很简单，但是它就是存在，然后我们都无法解释为什么。就是好嘛，那我们就说子弹极存在好了。可是你如果用狄拉克的看法，它这个螺线管它一定是一对的啊，你有没有可能把它，你就断开环节，然后让他们两个这样单独游走，是有可能的吗？狄拉克到他去世以前，他的解释只能到说，因为宇宙里面或是量子场里面发生了什么什么事情，导致那个螺线管看不到，但是那个连接它是断不开的。好 ，OK， 好，那我们最后来做一个 summary. This is the summary for the magnets, for the electromagnetism, and the part for the magnets. We added two important laws to the forces, to the space for the forces. One of them is the Lorentz Force Law, and the other one is the Gauss Law for the magnetic field. And here's just a comparison between Gauss Law for electric field and magnetic field. Yeah, I leave it here for a few minutes.哦，还在助教那 ，OK， 还在助教那，那你先记一下，然后我再请助教发还给你们。好。Okay, and here's another difficult chapter. So finally we come to the potential energy for the magnetic field. And there are two kinds of potential energy that can create magnetic field. Magnetic field can be created by electric potentials, and it can be created by the vector potential itself. 就是磁场的位能呢，这个问题我觉得非常的困难。然后呢，简单来说，它有两个来源，一个来源是电位能的变化，可以制造出磁场，这是一个。然后有另外一个呢，是磁场本身它也有一个位能，但是那个位能是向量，就是向量位能场。我们到现在为止，我们的位能都是纯量，就是 energy， 就是一个数字。但是磁场的位能它是一个向量。我不太确定磁位能是不是真的存在，但是在理论上它很好用。所以这个是关于磁场的位能的状况。好，那磁位能的部分，我看法拉第定律是一定会讲的，但是其他的比较困难的部分，我看我们的状况跟进度，然后我决定我到底要讲多深。Okay, so for the potential energies of magnetic field, so here the relation between magnetic field and electric potential, and this is actually the Faraday's law. So I will explain it anyway. And here the magnetic potential, the vector potentials, and I was given pictorial introduction, but how deep we go depends on our progress and depends on our schedule. So actually where we have schedule, we have electric circuits still, so we have to be a little bit quicker. Okay, so here is the video showing you how magnetic field induced electric potential.
We're going to have a look at Faraday's law of induction. For this demonstration, we've got a ring which consists of many turns of copper wire. Regrettably, it's covered with tape so they're not visible. It was known that when electricity went around a conductor, it produced magnetism. People had made electromagnets before Michael Faraday came along. If the magnet sits stationary inside the coil of wire, no electricity is made, and we can see that the meter needle is not moving. If the magnet is moved, the magnetic field within the coil of wire changes. And it is this changing magnetism that induces electricity. This is what Michael Faraday discovered. And notice that by moving the magnet in different directions, we produce electricity in either the forward or the backward direction. We can illustrate this with a bar magnet. The magnetic field of a bar magnet points away from the North Pole. And so we could imagine a series of magnetic lines coming from the north end with arrowheads pointing away from the North Pole and toward the South Pole. If I move that magnet into this conducting coil, I am increasing the number of magnetic lines that point in the direction I'm moving. So this is the reason that when I move a magnet in and out of an electric coil, I see my meter change directions and show me electricity moving first in one direction and then in the other. Another way to look at Faraday's law would be to produce electricity by induction and then use it. And so we've got an apparatus in which we have two coils, each of them placed vertically on the table. And above each coil is a magnet hanging from a spring. Magnets and springs are identical. If I move one of those magnets in and out of the coil, it will induce electricity. Second, we'll take a small battery and connect it to the second coil and see that when we put electricity into the coil, it produces a magnetic effect on the hanging magnet, and the hanging magnet moves vertically. So now we'll connect the two coils with wires and start bouncing the first magnet so it moves up and down at its natural frequency, producing electricity at that frequency. So the motion of the first magnet will be translated to the second magnet electrically, and we'll see the second magnet begin to move at the same rate as the first magnet because we are inducing electricity in the coil. The magnet doesn't just sit there, the magnet has to move.
So we just see how it, I think it delivers a lot of information at the same time. So let's go through it one by one. The first message in this video is like this. So if we have a bar magnet and just we have to pay attention when the magnetic field is going this way. So the magnetic field is weaker and it's getting stronger and stronger when it's closer to the head of your magnet. So, and here is another factor, because you are moving the magnet. So the strength of your magnetic field is changing with respect to time. So this is the important factor. The strength of the magnetic field is changing. And here you can see the increasing magnetic field strength. I have to say strength here but not light. Otherwise I'm confusing the others too. The magnetic field strength. And if you want to do it specifically, and actually we are calculating the flux of the magnetic field, so it's related to the direction and the strength at the same time, to be very specific. So the magnetic field strength or magnetic flux that point into the direction of the moving is increasing if you move your bar magnet this way. And this kind of movement create a current running on your wire. So this is the first important message in the video. 那在我们刚才看的那个影片里面，它给了你很多讯息嘛，然后每个都很有趣。我想要帮大家稍微整理一下。第一个重要的讯息就是，你观察一下，电流产生的要件是什么？它的要件其实是你现在手上有一个磁铁。你如果把那个磁铁就抓在那里一动也不动，什么事情也不会发生。可是如果你的磁铁一旦开始动之后，就会有电流跑出来。那我们去看那个磁铁动了这件事情，我们把它看得再深入一点。它有两件事情，一件事情是你可以想象你的磁铁它会制造磁场嘛，然后那个磁场呢这边是比较强，然后这边是比较弱，这里是比较强，所以你的磁铁 以这样的方向运动走进你的线圈里面的时候呢，它的磁场强度是从强变弱，弱变强，就是你的磁场强度就是会这样变强。然后再来第二个要件是，你抓着那个磁铁把它往前吐嘛，那你这边是有一个动作，然后它那个动作要完成有一个时间差，有没有？所以那个时间差也是重要。所以第一个是磁场的变化，它是从弱变强还是强变弱？然后再来第二个要件就是这个强弱变化是在多短的时间内发生的，所以这两件事情都会影响到你产生的电流的强度。好，这是第一个重要的讯息。然后呢 ，here's a schematic diagram for what I just described. So, when your magnet, this is the coil, and if you connect the coil into a current meter, and if you move your magnet into your coil, and here's the increasing magnetic flux, and here's the induced current on the coil, and you can always measure it. And here is okay, and here's another experiment, and it makes it a little bit complicated, but it's simply just the same concept, but it just converted backwards. So this is the moving magnet, which moves into or out of the coil, and it's inducing the current running on the coil. And you can see here is the wire which connects two coils together. So the current generated here on the right hand side is flowing to the other coil on with the connection of the wire. So here the current is flowing here again. So when the current is changing here, and the current on the other wire on the left hand side, and this side be increasing and decreasing like this again. So here you can see this is an oscillation. It creates the oscillating current, and here it just creates another oscillating current. The two currents are oscillating together, and the oscillating current creates the magnetic field, and then the magnetic field push and pulls the second magnet. So this is the story behind it. 好，这个实验看起来很厉害哦，感觉像灵异现象。然后呢，它要解释起来其实还有点复杂呢。就是你的磁铁在这里，磁铁跑进去跟跑出来的时候，它的磁通量一直在变化嘛。然后那个磁通量的变化，它让这个线圈产生了感应电流。然后呢，你可以看到磁铁的震荡造成的感应电流跟着它一起震荡。那如果你现在用两条电线把两个磁铁接在一起，那么这两个线圈是导通的。那如果说你在这里去做出了 induced current， 然后呢，在这里同时也会有震荡，也会有 current 的震荡，电流的震荡。然后这里的电流的改变，电流的震荡，制造出磁场，然后你就可以看到那个磁场就是它的方向就会跟着电流的方向一起改变嘛。然后呢，它就是去推动挂着的磁铁跟着一起上下震荡。所以呢，我们这里是把磁铁的能量转换成电的能量，传送到另外一边，电的能量又在转换成磁场的能量。好复杂，感觉很像在变魔术。Okay, so here's the upgraded messages in the video, and here's another experiment leading you to the numerical calculations. 这里是另外一个实验，然后这个实验它会告诉你要怎么样把我们刚才观察到的现象数量化。
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, And I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. And if I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also. We saw that as the number of turns in the coil increased, the current increased. So the current is proportional to the number of turns, which we'll use N to represent. We also saw that the current increased as the rate of change of magnetic flux inside the coil increased. So d psi dt represents the change in the magnetic flux inside the coil. Now, if we were to monitor the resistance of the whole circuit, that is of the coil and the wires and the ammeter, we would find that the current was inversely proportional to the total resistance of the circuit. Now, this equation is usually written as I is equal to minus N over R d psi dt. And we'll talk about the significance of this minus sign in a future video on Lenz's law. So now if we multiply both sides of the equation by R, we get Ri equals minus N d psi dt. And resistance times a current is a voltage or a potential. We call that the electromotive force. And so the electromotive force is equal to minus N d psi dt. And this is known as Faraday's law. Here's an illustration of the way Michael Faraday actually performed the experiment.
This is how Faraday did his experiment. You can look at it here. There are many documentary films on YouTube, you can watch it. 因为这个故事太经典了，你可以在 YouTube 上面看到很多关于这个故事的纪录片，就是我觉得还蛮有趣、蛮可爱的，你可以看一下。但是因为我们要赶进度，所以我们要稍微走快一点。But now we are behind schedule. I have to go a little bit faster. So here is a summary for our observations. So what are the factors that changes the current? So the number of coils. This is proportional to the amount of current. The speed of your move is proportional to the current. And the direction of the move. It definitely changes the direction of the current, right? So if let's just focus on the north pole of your magnet. If the north pole is going in, we get the positive current. And if the north pole is going out, we have negative current. And if the magnet is not moving, it just sits there, and if it's static, we don't have any current at all. And to summarize all of our discoveries, so we can arrange everything together and we get the Faraday's law. I think Faraday developed his theory that way, very empirically and just based on experimental facts. So the current is I, and we have the number of the coil, this is N, and the magnetic flux versus time, so this is the speed of the change of magnetic flux. And here is the factor resistance. We didn't test it in the video, but you can do the experiment by changing different materials for the wire. Yeah. So this is Faraday's law. And here is a negative sign. And this is from another law, which is called, this is from the Lenz Law. And the content of it is, if you use a bar magnet, and if you just push it into your coil, and in order to compensate the energy put in by the magnet, your coil is generating a current to create a opposite magnetic field to refuse to change. So that is a consequence of balancing energies, or a kind of action like inertia. Okay, so this is Lenz law. So the induced magnetic field is always in the opposite direction of your applied magnetic field. This is Lenz law. 冷次定律我们没有时间看实验，或者是去讲它比较深刻的定义。它的意思其实就是，它其实也是一个实验上的发现啊，就是你如果说拿着一根磁铁，你把它丢到那个线圈里面去，然后呢，你现在就是施加了一个磁场，然后为了抵抗那个磁场的变化，你的线圈就会制造出一股电流，然后那股电流会制造出一个电场反向的电场，就是跟你录进去的磁场要是相反的哦，因为它抗拒变化，它没事不想要改变。那它不想要改变产生的对策就是它会产生一个反向的电场，想要把你录进去的磁铁把它推开，不要进来，这样子。好，所以这就是冷次定律。好，那么这就是为什么我们这边会多一个负号，那个负号就是因为是冷次定律造成的。然后我们在之后讲电感的时候，你就会发现电感的行为就是跟惯性定律一模一样。它就是一股自然界的东西抗拒改变的倾向。Okay, so this is Faraday's law. And here. Okay, so here we'll do a little bit, we just do the imagination a little bit further. So if we move the resistance to the other side of the equations, and the current multiplied by the resistance is just equal to a voltage. But what exactly is that voltage? That voltage, we just call it the electromotive force. We just imagine this is the voltage which drives your current flowing in the coil. So the voltage of electromagnetic force, this is the potential energy that drives your current flowing. And you can see that the electromotive, this is a bit strange. This is voltage, but we call it force. So this is very, very confusing. You have to be very, very careful when you are using the terms. 然后大家要小心注意哦。虽然你这里说那个是 electromotive force， 但是其实它是电压。大家要小心。这都是它的起源都是早期的人其实没有把能量跟力这两个事情的概念分清楚，造成的混淆。但是我们现在已经分清楚了，所以我比较常用的字，我比较常讲 electromotive voltage， 我不太喜欢讲 electromotive force，that's too confusing。但中文里面有一个字是电动势，也是有一点奇怪啦，但是你要记得那个是能量，那是一股那是能量差，你要记得那是能量差。Change of okay, so you can see the relation between them. Okay, the voltage that drives the current, drives the charges moving, is proportional to the change of magnetic flux versus time. Okay, Faraday's law. Let's see if we can finish the example here. OK，我们把这个例子讲完。So let's finish this example. Though it's a little bit difficult, I find it. I find the example a little bit difficult, but let's finish it today. So here is a bar, and the bar is rolling on 2 wires. Here are 2 wires, and the current is flowing on the wire, and here's another wire which is connected to a resistor. Okay, and the green crosses are showing you the direction of the magnetic field. So the magnetic field now is pointing into the paper here right now. Okay, and we have to use Newton's law and find the speed of the bar as a function of the time after it is released. Okay, so now here is, we have to analyze the factors on it. We have the initial velocity at time is 0. And we have the velocity. Here's the current running on it. And the point is the current on the wire. And the magnetic field is creating a force, and the force is pulling your bar this way. And this is if you apply any forces on your bar. And when the bar is rolling on the rail, you can see that this is the area, and this is where the magnetic flux count for the induced current. 所以大家可以注意哦。这个问题就是，问题我好像有漏了一个字，但是它的状况呢，现在的状况就是，你如果说你有推一下你的金属条，然后那个金属条如果往右手边滚过去的话，然后呢，这个框框里面，这里有个面积有没有？然后这里在这个框框里面的电的磁场通量的变化，就会造成感应电流。好，然后那个感应电流呢，它就会产生另外一个力，然后想要把你的 magnetic bar 拉回来。好，所以这个就是实际上发生的状况。Okay, so now we have to analyze the forces and analyze the dynamics of it. First, we apply the Lenz Law. The bar is moving on the x direction. And here, this is Newton's law. So the force, the mass, and the acceleration. And from the Lenz law, and we can see that this is the force on the bar because of the current. And here's a negative sign because of the coordinate system. The direction of the force is giving you the negative sign. And this is just Newton's law. Okay. And what about the I? So what is the amount of the I? So this is the current, and we just apply Faraday's law. So this is the change of the magnetic flux, the number of the coil, and here is the resistance, and then this is the current. Okay, and now this is a simple system. We just have one round of the current. So now N is equal to I. R is just equal to the resistance here. And the magnetic flux is the magnetic field. And the L is the length of the bar. And X is the width of your closed loop. So this is X. This is L, and here is the area, and here, if you count the flux of the magnetic field inside, and then you have to look at the flux inside the closed loop here. Okay, and this is the change versus time. And constant, dx dt is giving you the velocity. Yeah, so this is the relation between the current and the velocity. And m dv dt, we are ILB. Okay, so this is ILB minus sine and I, and we are putting this one into the equation. That's it. And then the arrangement. And be careful about the sign. Here's a negative sign and here's another negative sign. So this is an example from the textbook. I'm not sure if the signs on the textbook is correct. So you can note it and you can correct your textbook later. And after all the arrangement, and we can get the equation of motion like this. dv over the velocity, a lot of constants, and this is time. Okay, and go on. So now we would like to know the velocity. So we have to do an integration on both sides. Integration on the velocity is from the initial velocity to the final velocity. And from time 0 to final time. And the integration of 1 over velocity is giving you a logarithmic terms. And this is the integration on time, it just gives you the time. And you can convert the logarithmic terms into regular numbers by doing the power of exponentials. This is a little bit fast. Yeah, I hope you can follow. I'm sure you can follow. Yeah. This is not very difficult. And the interesting thing is now you can see the velocity is changing in a exponential decay. Yeah, it's changing in an exponential decay, and the time constant of your exponential decay is related to these parameters. 好，经过这一连串推导，它有趣的地方是，你现在那根 magnetic bar， 然后呢，它是往你轻轻推它一下，然后它往我们的右手边这样滚过去嘛。但是因为你的磁通量增加，然后那股磁通量它其实是灌进来以后，然后我们的电流这一圈有没有就会冒出来，想要抗拒那个变化，然后抗拒那个变化，经过一连串推导之后，你就会发现你的 magnetic bar 滚动的速度会逐渐的减少，而且它减少的趋势是一个自然指数的衰减。Okay. So this is the magnetic force acting on a sliding bar. Okay. And here's the general form of the Faraday's law. Okay. So we have the coil, and the coil can be any kind of arbitrary shape. It doesn't need to be a square, it doesn't need to be a circle, it can be any kind of shape. But the point is just like this. You can see the potentials that drive your charge moving is just equal to the minus of the change of magnetic flux. So the electromotive force, the potential energies, you can calculate it in a way like if you measure the electric field on each point on your wire and you just integrate it along your loop of the current, then it's giving you the change of the magnetic flux. So this is the general form of Faraday's law for arbitrary shapes. 这就是如果你的线圈形状是很狂野，然后完全没有规则性可言的，你不要担心。就是这是 Faraday Law 的通用形式，就是你如果拿一个电表，你去量你的 coil 上面每一点的电场，然后呢，你就沿着你的线圈把你的电场积分起来，其实就是在计算电压啦。 对，然后呢，你就会发现它一定会等于磁通量的变化，但是你要加一个负号，因为冷磁定律，因为电流产生是它要抗拒变化。好 ，OK， and here's this example. Let's do it next time. Yeah, that is an important example, so let's do it next time. Okay, so the lecture is up to here today, and let's do it. Let's continue next Tuesday. Yeah. 我们今天上课先上到这边，下礼拜2再继续，因为这个还蛮重要的。